Look up. At night, a giant, gleaming disk hangs in the sky. It's been there for as long as humans have walked the Earth, a silent, watchful guardian. We call it the moon. Our moon. But how did it get there? Where did this celestial companion come from? The birth of our moon is a tale woven from cosmic collisions, scientific debate, and tantalizing mystery. For millennia, humans have gazed at the moon, weaving myths and legends around its silvery glow. Ancient civilizations saw gods and goddesses in its craters, told stories of moon rabbits and lunar festivals. But it wasn't until modern science that we began to unravel the true secrets of our celestial neighbor. We learned that it wasn't a god, nor a piece of cheese, but a giant ball of rock, trapped in Earth's gravitational embrace. But that discovery only deepened the mystery. How did this giant rock get there? What cosmic dance led to its creation? We've walked on its surface, planted flags, and brought back pieces of its desolate beauty. Yet the origin of our moon remains one of the most captivating puzzles in astronomy. Picture this: the early solar system, a chaotic nursery of newly formed planets and rogue asteroids. Earth, still in its infancy, is a molten ball of rock, its surface a fiery ocean of magma. Then, a Mars-sized object, Theia, appears on a collision course with our fledgling planet. The moment of impact was a cosmic symphony of destruction, an event so cataclysmic that it boggles the mind. The impact sent shockwaves rippling through both bodies, shattering Theia into countless fragments. From this chaotic cauldron, our moon would eventually emerge. In the wake of the cataclysmic impact, the space surrounding Earth was transformed into a swirling inferno of molten rock and vaporized metal. The debris, propelled by the sheer force of the collision, orbited the Earth in a chaotic dance, forming a glowing ring of superheated material. This ring, known as a synestia, was a short-lived but spectacular phenomenon, a testament to the violence of the moon's birth. Within this ring of fire, the process of accretion, the gradual accumulation of matter under the influence of gravity, began to take hold. As the debris cooled and solidified, tiny particles began to clump together, drawn towards each other by their mutual gravitational attraction. These clumps over time grew larger, forming moonlets, small, rocky bodies destined to play a crucial role in the moon's formation. Imagine this early solar system, a celestial shooting gallery with these moonlets like cosmic billiard balls colliding and merging. Each collision added to their mass, their gravitational pull increasing with their size. As they circled the Earth, these moonlets swept up more debris, their orbits intersecting and overlapping in a chaotic ballet. Over thousands of years, this process of collision and accretion sculpted the moon we know today. The early moon, born from violence and chaos, was a far cry from the serene orb we see in the night sky today. Its surface was a molten ocean, constantly bombarded by meteorites and asteroids. But slowly, over millions of years, the moon began to cool and stabilize. The molten surface solidified, forming the familiar dark plains and rugged highlands we see today. The giant impact hypothesis, while compelling, has its critics. Some argue the impact should have left a distinct chemical signature and point to angular momentum discrepancies. Recent studies support the theory, uncovering subtle clues in lunar rocks. Analysis of Apollo lunar rocks shows isotopic similarities to Earth's mantle. This isotopic fingerprint suggests a shared origin, pointing to a common ancestor. Scientists found remnants of Theia in Earth's mantle, hinting at a core merger. While the giant impact hypothesis holds a prominent place in lunar origin stories, it's not the only contender. Some scientists propose an alternative narrative, where Earth and the moon formed together. This theory, known as the double planet hypothesis, suggests a more crowded, chaotic early solar system. Earth and the moon formed in close proximity, each accreting material from the same region. This explains the moon's isotopic similarity to Earth. Another contender in the lunar origin story is the capture theory. This theory proposes that the moon formed elsewhere and was later captured by Earth's gravity. Earth's gravitational pull, like a cosmic lasso, snags the moon, pulling it into its orbit. This scenario, while dramatic, presents significant challenges. The capture theory struggles to explain the moon's isotopic similarity to Earth. Could our moon be a larger, more dramatic example of such a capture? Each theory of lunar formation presents its own set of strengths and weaknesses, a cosmic tapestry woven from scientific evidence, educated guesses, and a healthy dose of speculation. The giant impact hypothesis, while widely accepted, still leaves some questions unanswered. Why, for instance, does the moon's composition so closely resemble Earth's mantle, rather than a mixture of Earth and Theia's material? And why is the Earth-Moon system's angular momentum lower than predicted by some impact models? The double planet hypothesis elegantly explains the moon's isotopic similarity to Earth, but struggles to account for the differences in their iron core sizes. How could two bodies forming side by side from the same material reservoir end up with such distinct internal structures? And could the early solar system, a chaotic and violent place, have provided a stable enough environment for two large bodies to form so closely together? The capture theory, while statistically improbable, cannot be entirely ruled out. Could our understanding of planetary dynamics and gravitational interactions be incomplete, overlooking mechanisms that might make capture more likely? The quest to unravel the moon's origins is far from over. It's a journey driven by scientific curiosity, fueled by technological advancements, and guided by a deep-seated desire to understand our place in the cosmos. Each new mission to the moon, each analysis of lunar samples, each refined computer simulation brings us closer to a complete understanding of our celestial companion's birth. Perhaps the true story of the moon's formation lies in a combination of these theories, a hybrid model that incorporates elements of giant impacts, co-accretion, and even capture. Perhaps the early solar system was even more chaotic and unpredictable than we currently imagine. A cosmic maelstrom where multiple events, collisions, and gravitational interactions all played a role in shaping the Earth-Moon system we know today. As we delve deeper into the mysteries of the moon, we learn not only about our celestial companion, but also about the formation and evolution of planetary systems throughout the universe. The moon, once a distant object of wonder, becomes a scientific laboratory, a window into the early solar system, and a testament to the power of scientific inquiry to illuminate even the most enduring cosmic mysteries. The Earth-Moon system, with its unique characteristics and complex interactions, provides a fascinating case study in celestial mechanics and planetary science. Unlike any other planetary body in our solar system, the moon is unusually large relative to its parent planet, Earth. This unique ratio has profound implications for how we understand both bodies. The current theories regarding the moon's formation help explain some of these peculiarities, but also invite new questions about the dynamics and history of our own planet. Given the moon's significant size compared to Earth, it exerts considerable gravitational influence, impacting everything from the tides to the length of a day. The synchronous rotation of the moon, where one side always faces Earth, also reveals the historical gravitational interplay between the two bodies. This configuration suggests a violent history marked by close encounters and massive impacts, which have given rise to the current stable system we observe today. Our understanding of the Earth-Moon system is not just academic. It influences everything from our calendars to navigation systems. The precision with which we can measure the distance to the moon, for instance, has led to improvements in GPS technology. Additionally, studying the Earth-Moon system provides clues about other planets and moons in our solar system, offering a blueprint for understanding complex gravitational interactions in exoplanetary systems. The moon's influence on Earth extends beyond orbital dynamics and enters the realms of geology and climate. The formation of the moon, resulting from a colossal impact, not only affected the physical structure of Earth, but also played a crucial role in the evolution of its atmosphere and oceans. The moon's gravitational pull is primarily responsible for the tides that rhythmically sweep our planet's shores. These tides have been a critical factor in the mixing of ocean waters, which affects both oceanic and atmospheric temperatures. The presence of the moon is also thought to stabilize Earth's tilt, and consequently, its climate. This stability has likely been essential for developing complex life, providing a relatively stable environment over geological timescales. Without the moon, Earth might have experienced more drastic tilts, leading to severe climatic extremes. Such stability is relatively rare in the cosmos, further highlighting the unique nature of Earth's relationship with its satellite. Moreover, the Moon's impact on Earth's evolution is a vibrant area of study that continues to evolve with every new lunar mission. The samples returned from the lunar surface provide direct evidence of the Moon's violent formation, shedding light on Earth's early history. These insights help scientists understand not just the Moon's formation, but also the processes that have shaped Earth's geological and atmospheric layers. While it might seem less intuitive, the Moon's influence extends into the biological realm as well. The life cycles of many marine animals, for instance, are synchronized with the lunar cycle. The reproductive activities of numerous marine species, such as corals and some fish, are timed with the phases of the Moon. These adaptations suggest that the Moon's phases can act as a cue for biological activities that are crucial for survival and reproduction in these species. Furthermore, the lunar cycle has been integrated into human culture and timekeeping, influencing agricultural practices and mythologies around the world. This cultural integration hints at a deeper biological connection, potentially affecting human behaviors and physiological processes. Studies have explored how the lunar cycle might influence sleep patterns and mood, although results are often debated and not conclusively proven. The study of these biological rhythms in relation to the lunar cycle not only enriches our understanding of Earth's biosphere, but also opens up questions about life's adaptability to extraterrestrial environments. As humans plan for long-duration lunar missions, understanding how the lunar environment affects biology will be crucial for the success of such endeavors. Looking forward, the Moon and future space exploration. The Moon continues to be a focal point for space exploration and scientific research. It serves as a stepping stone for missions further into the solar system, and potentially as a site for future human colonization. The implications of the Moon's formation theories extend into how we plan these missions. Understanding the Moon's geology helps us prepare for the challenges of lunar bases, from building materials derived from lunar regolith to managing exposure to cosmic rays and microgravity. Future missions to the Moon, like NASA's Artemis program, aim to establish a sustainable human presence on the Moon by the end of the decade. This ambitious goal is driven by a desire not only to explore, but to utilize the Moon as a laboratory to study planetary sciences, including the effects of living in space on the human body. Such studies will pave the way for future human missions to Mars and beyond, providing critical data on space travel's physiological and psychological impacts. Furthermore, the continued exploration of the Moon has the potential to unravel more about the early solar system's history, offering insights into planetary formation theories and the dynamics of celestial bodies. The Moon, a chronicle in stone and dust. The Moon, our celestial dance partner, has witnessed Earth's evolution for billions of years. Its cratered surface whispers tales of cosmic collisions and planetary formation. The Moon's existence challenges us to delve deeper into the mechanics of the universe. It becomes a tangible link to our planetary past, a Rosetta Stone etched with history. The Moon is a laboratory, a time capsule, and a source of inspiration. It encourages us to look up, ask questions, and never stop exploring. Our cosmic backyard, a springboard to the stars. The Moon, once an unreachable destination, has become our cosmic backyard. It's a training ground for future missions to Mars and beyond. Every mission adds to our understanding of this celestial body. These lessons pave the way for more ambitious missions. The Moon is now a stepping stone for humanity's next giant leap, inspiring generations to come to reach for the stars. Eyes on the sky, feet on the Moon. The Moon's formation is a testament to scientific inquiry and our relentless pursuit of knowledge. From ancient astronomers to modern scientists, our fascination with the Moon is constant. Exploring the Moon reminds us of the universe's mysteries. Each discovery leads to more questions and a deeper appreciation for the cosmos. The Moon, in its silent orbit, beckons us to explore and never lose our sense of wonder. When you look at the Moon, remember it's a cosmic mystery and a testament to human exploration.